trees or heaps. We have an example of such a program on the left. It has one method main. It takes two arguments, a list x and an integer variable I. The integer variable I is supposed to store the length of the list. And the program in a non-deterministic while loop, it keeps removing elements from the head of the list and decreases the variable I accordingly. And it is asserted that whenever you exit the loop, the length of the list is positive. We are interested in proving that this assertion always holds, and we are interested in doing it automatically. So, if you want to capture this program quite formally, a good starting point would be using algebraic data types to encode your data types, like lists or trees. And of course, when you have algebraic data types, you also need recursive functions to capture the properties such as length of your data types. And how would you prove this program is safe? Well, you have to come up with an inductive invariant. An inductive invariant is a formula that is true at the start of the loop, the first iteration of the loop. And if you assume that it's true at the start of an arbitrary iteration, you can show that the inductive invariant is true at the end of the execution. Inductive invariant is also strong enough to prove the assertion that you want to prove. An example of such an inductive invariant is that I is actually indeed equal to the length of x. Okay, so the primary focus of this paper is how do you automatically come up with such inductive invariants, especially in the presence of algebraic data types and recursive functions. The pipeline that we are going to be using is we are going to translate the safety problem into one of solving CHCs. This is automatically done using some value condition generator. It will generate some CHCs, and then we solve the CHCs using a CHC solver. The CHC solver is going to solve CHCs, and it's going to tell you whether the CHC is satisfiable, which means that the program is safe, in which case there exists an inductive invariant, and the CHC solver is going to give you the inductive invariant that will prove the safety of your program. Or the CHC solver is going to tell you that the CHCs are unsatisfiable, in which case your program is unsafe, and the CHC solver will give you a counterexample that validates the assertion. This sort of pipeline of translating your program to CHCs is becoming more and more popular. There are many tools that translate many imperative programs into CHCs. Of particular interest to the Perl community would be recent work that does type inference using CHC solving. This work is focused on the solving aspect of this pipeline. So, what exactly are constraint horn clauses? Constraint horn clauses are a fragment of first order logic. These are constraints over some uninterpreted predicates. Of course, there is this additional requirement that all constraints are horn clauses, which means that you only allow at least one positive literal in a clause. Without properly defining constraint horn clauses, I'm just going to illustrate it using an example. Recall the program that we had on the first slide. If you translate it into CHCs, this is what you would get. Importantly, there is an uninterpreted predicate called in. That is what we are solving for. It has three constraints. The first constraint encodes the requirement at the start of the loop, that is length of x equal to I. And the second constraint encodes the body of the while loop. And the third constraint encodes the assertion. Of course, since your program contains algebraic data types and recursive functions, the CHC also contains these two things. What exactly are solutions to CHCs? As I mentioned earlier, a solution is would be an inductive invariant for the program. It is any interpretation of the uninterpreted predicate that satisfies all the constraints. We also require that this interpretation is expressible in some language. An example of a solution would be the interpretation index I equal to length of x equal to I. So if you substitute function is a little bit weird because you have this uninterrupted predicate and you're saying that it is equal to a recursive function applied to some argument. Unfortunately, when you solve constraint on clauses modulo recursive function, you might have to come up with these recursive functions. For example, think of when you're writing a program that manipulates data types and you have to write a looping variant. Sometimes the looping variant might talk about properties of the data types that are not present in your program at all. So sometimes you have to synthesize entirely new recursive functions in order to prove these properties. Once you synthesize a recursive function, you have to apply it to proper arguments. And finally, once you have recursive function applications, then you need to construct solutions using those recursive function applications. In our case, we did not have to synthesize the recursive function because it was already in our classes. But we had to figure out that we had to apply the recursive function to the argument x and not to something else. And then finally, we had to construct the whole solution, length of x equal to I, from the recursive function application, length of x. These are two orthogonal problems. First problem is about synthesizing recursive functions, and the second problem is about finding solutions using the synthesized recursive function applications. We are primarily interested in finding solutions, and we assume that a third-party oracle already synthesized the recursive functions during the VCGen phase of CHC solving. How do you do that? How do you encode recursive function applications in CHCs? So what we want is that we want solutions that do not contain recursive functions, like length of x. And what we can do is we can use ghost variables to encode recursive function applications that we know are going to be in the solution. For example, the example that we saw earlier had length of x in the solution, and we want to generate a new set of Hahn clauses such that its solution does not contain length of x. We can achieve this by storing length of x in a new ghost variable. In this case, we use a variable j to capture recursive function application. And you augment the uninverted predicate to take this as a third argument. So the point is that once you do a transformation, you can search for solutions that do not contain recursive function applications. Okay, so let's say somebody does that for you, that is, somebody encodes all necessary recursive function applications for you. Then the next task is to search for solutions of the constraint Hahn clauses. And that is going to be the rest of the talk. Why is this hard? Well, it is hard because recursive functions are hard. Recursive functions often require inductive reasoning. For example, if you want to prove that the length of a list is positive, it's an inductive argument. And recursive functions are also undecidable. Now this adds to our source of undecidability. Recursive functions without any uninterpreted predicates are undecidable, and constraint Hahn clauses without any recursive functions are also usually undecidable. So these are the two challenges we address in this work. Before we get into our contribution, this is what is usually done to avoid these two problems. It's called relationification. What it is you basically encode the recursive function as a set of constraint Hahn clauses. So you replace the recursive function with a new uninterpreted predicate that summarizes the recursive function. To take an example, consider the program that we saw earlier. The constraint Hahn clauses are like this. If you replace all recursive function applications with a new uninterpreted predicate, this is what you would get. So you replace all literals length of x equal to j with the atom length xt. Of course, length xt is a new uninterpreted predicate. We have to constrain it further using the definition of the recursive function. Okay, so let's say you do this, and now you have a system of Hahn clauses that does not have any recursive functions. What are its solutions? The solutions involve an interpretation for both unindependent predicates in as well as length. One possible solution is what is shown in the slide. We keep the same solution for in, and for the solution for length, we just give the actual definition of length. That is, you map all possible lists to their lengths. Of course, the solution is not expressible. We might have to come up with a succinct summary of length. For example, j greater than or equal to. Okay, so this is what is currently being done. The good thing about this is that this transformation preserves satisfiability. And since you have recursive functions that since you have uninterpreted predicates that capture recursive functions, you get indictive summaries. However, the bad thing is that we show that sometimes there is no satisfiable summary that is expressible in our language. The first contribution of our paper is to formalize relationification and then show that while relationification preserves satisfiability, it does not preserve solutions. In other words, we need recursive functions. We can't just get rid of that. So, second contribution of this paper is a pipeline for solving CHC's modular PDGs and RS. The first step in the pipeline is to relationify the recursive functions, and the next step is to add back the recursive functions that you replaced. Now you have a set of constraint clauses containing both recursive functions and relationified predicates. Relationified predicates helps you come up with indictive summaries, and original recursive functions helps you preserve solutions. And the last step in the pipeline is an algorithm for solving CHC's FF. Let's take a deeper look into what CHC's FF are. This is the set of relationified CHCs that we saw earlier. Adding back a recursive function is literally that. So for each predicate application length xi, you add back the literal length of x equal to r. The good thing about the system is that you can use length xi to infer indictive summaries of recursive functions. And since you have the original recursive functions, you don't miss any solutions. But it has the same problem as we started with. It has two sources of undecidability. To overcome undecidability, we use two forms of abstraction. The first form of abstraction is recursive function application, recursive function abstraction. What it does is it unrolls and replaces recursive functions with uninterpreted functions. So let's say you have a term length L. You replace length L with its definition. In this case, it's a match expression. Of course, since length is recursive, you will have other occurrences of length in the definition. You unroll it again by replacing length T with its definition. And you do this until you're satisfied. And finally, you replace all remaining recursive functions with a new uninterpreted function. The good thing about this abstraction is that after you do this abstraction, you only have to reason about uninterpreted functions, which is decided. In our paper, we show that if you apply this abstraction to the CHCFF, what you get is a hierarchy of constraint clauses. The more unrolling you do before the abstraction, the more solutions you get. So this hierarchy means all the, it's the best of all worlds. It has uninterpreted predicates to summarize, to get indictive summaries for recursive functions. It has more solutions than just relationification, and we don't have undecidability because we replace all recursive functions. The second abstraction we use is the uninterpreted function abstraction. It simply removes all uninterpreted functions from the formula that you're talking about. As we'll see later, it is used to remove uninterpreted functions before quantified definition. The last part of this talk is our last contribution, which is an algorithm for solving CHCFF. The algorithm is called Spacer, it's called Racer. It is based off of Spacer, which is an IC3 PDR style algorithm, and it employs the two abstractions that I talked about earlier. explain a little bit about Spacer. Spacer is, as I mentioned, it's an IC3 style algorithm that searches for solutions to CHCs. It works by recursively blocking proof obligations. Proof obligations are bad states or predecessors to bad states. You think about states that violate the assertion that is in your program. Any state that violates the assertion or any states that can potentially reach the state as a proof obligation. Spacer works by recursively blocking these proof obligations. This is the crux of the Spacer algorithm. What it does is, given a proof obligation, it will generate predecessor proof obligations. Predecessor proof obligations are any program state that can get into a bad state in one iteration, in one step of your program. Once it generates predecessor proof obligations, it will recursively try to block them. And if it is successful in blocking them, it will learn a lemma. And hopefully, after it learns enough lemmas, the lemmas are enough to block the original proof obligation. If not, it will compute a set of reachable states which may intersect with the proof obligation, proving reachable. And this is a bit too high level. I'm not going to go into details of how Spacer works. It is enough to understand that all, all these blocks involve SMT queries. For example, if you want to check whether a set of lemmas block a proof obligation, it is a query to an SMT solver. If you want to generate predecessor, it is a form of quantified elimination. Spacer uses an algorithm called model-based projection in order to do this. So, what are the main differences between Spacer and Razor? The problem with solving CHCs or recursive functions is that whenever we want to block a proof obligation or we want to check whether something is reachable, you will have recursive functions, which means that if you make a query to an SMT solver, you will be in an undecidable fragment, which means that the SMT solver need not come back and tell you sat or unsat. So Razor smartly employs the two abstractions that we talked about earlier in order to prevent us being in an undecidable fragment. So whenever Razor makes a query to an underlying SMT solver, it employs either a recursive function abstraction to make things in a decidable fragment, or it will employ uninterrupted function abstraction to make sure that there are no uninterrupted functions when you do quantified elimination. Unfortunately, we won't have more time to go into either the Razor or the Spacer algorithm. Please read the paper for more details. The good thing about Razor is that since it makes no undecidable queries, it is guaranteed to terminate whenever the set of constraint hook clauses is unsatisfied. That is, if your program has a bug in it, Razor is sure to terminate and tell you that there is a bug. We implemented Razor on top of Spacer and made it open source. We evaluated on two sets of benchmarks. One is a set of imperative REST programs from the restaurant tool, and the other is a set of functional programs encoded by the Debug tool. There are actually quite a few tools in this area that solve constraint on process module recursive functions. Unfortunately, I did not have time to go into any of these related work. It is sufficient to know that we are better than most of the competitors. That's it. Thank you.
Thank you. Questions from here? We can have one online. Yep. How does this work compare with the invariant generation using separation logic with inductive predicates for heap manipulation programs?
Okay, interesting. I'm not completely aware of that. Like, I have been interested in separation logic for quite a while now, but I have not directly tried to compare this to any of the separation logic works. But thank you, that's a good point. I should definitely do that.
Another one? Yep. how to specify the templates of the invariant, namely how to determine the inductive predicate, such as the numerical measure in your examples.
What do you mean by templates? So let me just take this. Do you mean how do you do this? That basically how you
Yeah,
develop?
yeah, I think so. I think so.
Okay, so in the evaluation, we did this completely automatically. That is, for each recursive function in the program and for each algebraic data type in the program, we just used term abstraction for each of those pairs. This is a greedy approach and is quite unnecessary. The point is that you can do this automatically. So in our evaluation, we did this completely automatically. If you are a user of this tool, maybe you can come up with a smart heuristic for your set of benchmarks. But once again, you don't have to do it completely manually. You don't have to know the solution. You can do this greedily and just say, okay, I'm going to apply all sorts of recursive functions to all sorts of algebraic data types and just let the CHC solver deal with it.
Okay. There's another question online. With an interpreted functions in the base case, how do you prevent that they are interpreted arbitrarily, namely constant zero?
Are you talking about relation integration? Not quite sure I understand the question. Can you repeat the question again?
With uninterpreted functions in the base case, how do you prevent that they are interpreted arbitrarily?
Okay, so I'm assuming that the question is referring to the recursive function abstraction.
Yeah.
Um, you will not have uninterpreted functions in the base case, especially because it is the base case. So the base case will not have any other uninterpreted functions. But whenever you have uninterpreted functions, okay, we go into quite a lot of detail in the paper about how you deal with uninterpreted functions in constraint on clauses. The point is that the uninterpreted functions are universally quantified, and whatever solution you come up with is going to satisfy all the constraints you have. So yes, uninterpreted functions are arbitrarily interpreted, but it does not affect our soundness.
Okay.
Does that answer the question?
I think so. Well, at least for me. But they didn't raise the question. Is there anyone here from the audience? Another one online? Yeah, another one. Do you think it would be possible to integrate Racer's approach with work like Leon that also uses a provided logical approximation for the function?
Yeah, so in our evaluation, we do compare against benchmarks that are generated by Leon. So my understanding is that if you are wanting to use Leon, you have to provide these heats, like you have to provide inductive invariants in order to verify the program. And we are trying to do this completely automatically. And yes, we do want to eventually do that. So we want to integrate with systems such as Leon or Daphne, where if the CHC solver cannot find an inductive invariant, then the user can step in and say, okay, this is an inductive invariant. Try to check whether this is useful or not.
Okay. I think we are perfectly in time. So thanks the speaker again